And what I'll go through is I'll give a little motivation on why this is needed. Then I'll talk about some existing systems. And then I'll talk about Netcatch, which is what we call it when we don't want to say the full title. Call the system. Then I'll talk about an operation scenario and how it works. And then I'll show some simulations, which are done with Dune and Neptus. I'll talk about Linecatch, which is a little an extension of it. And then I'll talk about some practical challenges and some future work. So the motivation for it is the need or that we want to use fixed wing UAVs from ships. And when you have a normal fixed wing UAV, landing it on a ship is a challenge because you would either need a big runway like a hangar ship, which you don't have access to usually, or you need some mechanism to land this fixed wing UAV on the ship. And why we want to use fixed wing UAVs is of course that they have long range and can carry a heavier payload than multi-rotors. So yeah, the challenge is to land them. One way to do it is to land it into a net, as shown here with Portos, with these X8 that we saw in the lab earlier. So you can land it into a net that's fixed on the ship. Another way is to use a VTOL aircraft, so it can land like a multi-rotor but transition to fixed wing flight in air. Then there's some commercial systems. There's the Scan Eagle, which uses a hook on the wingtip and a vertical line on the ship for landing, or for recovery of the UAV. Then there's also DARPA is developing a system called Sidearm, and I'm not sure this will be commercially available, probably not. But they basically have a hook on top of the aircraft, and then they are flying under an arrest mechanism, which is on this boom hanging out of the side of the ship. And then there's zipline, which is not used on ships, but it's used by a company delivering blood to hospitals in Africa, Rwanda, I think it is, but I'm not sure which country. And they basically use a hook on the UAV, and they have two poles with a string between them, and then they fly into that one. And as far as I found out, they use some coordination or move the poles according to where the UAV is flying, and they use some sort of computer vision for that, but it's not something that they want to share with people. So this is a proprietary system. But it could be used on ships because it doesn't take a lot of space for landing the UAV. So, on to Netcatch. Now, first I'll say that some of the problems with these systems are that either they are proprietary and you might need some heavy modifications to the UAV. So VTOL is a heavy modification to a fixed-wing UAV frame. The Scan Eagle, you'll need a very rigid structure to land it by flying it at landing speed, but with the wingtip into a line. Most UAVs, you would just tear the wing off the body, and yeah, you wouldn't have recovered the whole UAV, just pieces of it. And the DARPA sidearm as well, you also need a very high precision there of flying, as far as I've seen. Whereas the net landing is very feasible, but if there's wind, then you have turbulence from the ship's superstructure, and you might not be able to align the net as you wish, so you might need to land in crosswinds because you can't take up the whole area of, you might be restricted in area where you can land and from what direction of the ship. Yeah. So that's what this system is trying to solve. And what it is that it's two multi-rotors holding a net, shown here, and you can't see the actual net. You can see two rods holding the net, an upper and a lower, and then this net is kind of between the rods. And the fixed wing flies into the net, as you see, and it's then caught in the net. And it has some small hooks on the fixed wing for now to make sure it stays in the net when it's there. Yeah. So, oh, that changed in a strange way. Let's see if we can. No. Yeah. So I have a little video here if you want to, yes, it's loading, how it looks. And these are some field experiments done as part of a PhD project where they tried this concept the first time. And that is then the concept that I'm trying to work more on. So as it is shown here, only the actual landing part of it is done automatically. So the takeoff is done by pilots, and about now it's switched into automatic mode, and it communicates with the aircraft, and then you'll see the multi-rotors coordinating their position in order to catch the aircraft, and then you have a successful catch, after which the pilots will again take control, and they will then land the aircraft. Let's see. Yeah. So, and you might notice there's some wobbling of the formation of the multi-rotors. So this is basically, at this stage, it is working 80% of the time. And that's, of course, the challenge to get it to work more. But here you see the pilots lowering the multi-rotors and releasing the net, and now they land the multi-rotors individually. So you have two pilots landing the multi-rotors, and you need a third pilot for the plane. Even though it's flying, you need like a safety pilot to take over. Yeah, so it was done by Christian Clausen, the PhD at NTNU, and you also saw the pilots. Yeah.
Stick pilots on the multi-rotors.
Yes.
For takeoff and landing.
Yes, but that is done.
They switch to autonomous mode, and the two vehicles are tracking the incoming.
Yes. Yes, correct. And then after it's caught, the plane is caught, then you switch to manual mode again, and you lower the aircraft and you release it, and then you land the multi-rotors individually. So while the multi-rotors are in the air, until you have released the plane, they are flown only by one pilot who control the position of or the velocity of the formation of multi-rotors. So the two pilots don't have to, the second multi-rotor pilot is only there for safety reasons, yeah, and for landing the multi-rotor when in the end. Yeah. I hope that clarified. Yeah. No, we are not. Oh. There we go. Okay. So, and yeah, this is the operation scenario which we have kind of gone through. So, number one, you take off the multi-rotors from the ship. Then you go to the desired area where you want to recover the fixed wing, which is shown as number 2. And you, of course, you can align that so you're always landing into the wind. And this is one of the advantages of this system. And then after you caught the fixed wing, you land it on the ship again, as you saw in the video before. So this is just how to do that, use this on a ship. In order to make this work, you have communication between the vehicles, and as it was done here, you have the fixed wing is flying its own plan while it is transmitting its location and velocity to the multi-rotors, and then they will then in turn coordinate with the plane, so they catch the plane while they keep the formation of the two multi-rotors. So they have need a lot of communication between each other and some communication from the plane as well. And everything goes through operator interface on the ground. So, and as you saw on the video, the multi-rotors were moving in the cross-track plane in order to catch the UAV, fixed-wing UAV. But they were also coordinating, as you see this is the laser. Yeah. So they were also moving a long track for the plane. And you see here, when the plane reaches some set distance from the multirotors, they start moving towards the desired point of recovery. So, and then they reach this point of recovery at the same time as the plane. And while they reach this point of recovery, having some velocity along track. And the reason for doing that is to lessen the impact on the net, which to save the airframe from stress, and also to not have a huge pull in the or huge forces on the multirotors as you recover the plane. So this is to smoothen everything out. Yeah. So here it is simulated in Neptune. I don't know if you can see the plane is here. The multirotors are up here, and now they are coordinating. The plane is not able to follow the track that it's supposed to, so it's going a little bit on the side, and the multirotors are now coordinating themselves. And as in this simulation, the actual catch is not simulated, so the multirotors are just continuing. They think they missed the plane, and the plane just continues. So some of the things we can see here in the Neptune interface is the position of the plane, I believe, and of the net. So here the multirotors are coordinating, and then they are catching the plane. And now you can see the plane continuing because the simulation doesn't take into account the actual, or doesn't simulate the actual catch. Yes? Yes?
Do you have a plan for when you fail the catching?
Yes. So you have different abort plans, which you can do in case of like an error, where you actually have to abort, and sometimes it's enough to just move the net, or you might have to release the net if you have measured too much force on the net or something like that. But as it's made here, the plan for if you don't catch it is just to return to your initial position and try again. Yeah, the plane will go around again. But as it is now, the plane plan and the multirotor plans are separate. Yes, and that is also done in order to be able to use, if you want to use the Marvelink console and fly it via only autopilot the plane, then you can also do that as long as you get the position and velocity information that you need. Yeah. So developing this Netcatch, there was also an idea to extend it and do Linecatch instead, which is kind of a tweak on it, where you have a line between the multirotors instead of a net, and you have a line hanging down from the plane with a hook on it. So when these lines cross, then the hook grabs the line between the multirotors, and you have then caught the plane, and you can fly it back. And one advantage of this is that there will be less drag on a line between two multirotors than between a net. So you might have to use less energy on doing this in windy conditions, because you don't have a net, which is a huge sail actually dragging you around and being pushed by the wind. You can use the lines instead. So because it's lighter, and also that you might be able to suspend a bigger line, so you have less requirement of precision in the recovery. So yeah. Yeah, I mean, for now the net is also suspended by lines, so I'm not sure if it will swing more. Yeah, it might, yeah. Yeah, another advantage of this could also be that the pitot tube from the plane could get caught in the net and ripped off or bent and broken, and that's kind of expensive equipment, and you don't want to break that all the time, every time you land. And that wouldn't happen here, as it will only be a line hanging from the plane that would actually have contact with anything. So we did some tests here of just the concept. And here, this is from, there's a second video afterwards, but this is basically a line, and there the plane is coming with a line hanging under it, and it's caught. So here we're having the line suspended between two poles just to test how it would mechanically work. And here you see it from the side, or from in front, so you see the two poles, and you see the line and the plane. And these are manually piloted tests, where, of course, you don't have, these are not, like the poles are not moving, so you have a kind of a hard impact compared to what you would have if you had the two multirotors coordinating it. No, we didn't measure that, yeah. The multirotors? Yes. Yeah, and if you compare it to the Netcatch, we have a pole on top of the net, and you had more vertical lines up to the multirotors. So then you would use a lot of energy just to lift it, and the pole would provide the structure for making the forces go upward. Here you would basically, if you need the multirotors like that, you would use a lot of energy just pulling them apart to keep the formation. Yes, so that is definitely something we're thinking of, and that's also why we haven't tried this with multirotors yet, because it's a challenge. So you'd have to move your multirotors closer to each other as soon as you caught the plane in order to have a more vertical line of the force from the plane. Or that's at least the strategy. No. Just on. Yes, but I think you can do it with the base moving as well. Yeah. So, sorry. No, I think you can do that, yes. As far as I'm aware. We also have a project at NTNU where we want to do an automatic landing of an X8 into a net on a ship, a stationary net, using RTK GPS on the ship and on the plane, and on the net as well. So we can use that to kind of coordinate with the plane. Yeah. So talking a little bit about the actually having a line hanging from the plane here. We don't want that all the time, and so now we've had a master project with a master student where he developed a little pod that can open up and let out a line, and then you can also release the line again if you are, let's say you're not able to do the line catch and you want to do a manual landing. If you have a line with a hook on it and you want to belly land in grass, then the hook will grab the grass, and you would have a harder landing than you were actually supposed to have. And yeah, we have done these tests with the hooks and landed in grass as well, and the plane survived, but it gets pretty beaten up. I mean, it's not something you would do with expensive instruments on board, at least. So if the master student has built a little model of how the line is going to hang in order to, so we can choose which lines to use, and we've compared it with a video of the plane, which shows that the model is not perfect, but for now we are only going to use it to choose the line and the hook and the weight on the bottom of the hook in order to have the line hanging far down below the plane. So we need a small precision in the landing, which was important for the piloted landing, especially important there because it's difficult to fly it. All right, so some of the practical challenges were tuning of the formation controllers in order to keep the nice formation. We've now achieved a much better formation than what was shown earlier, which is a little bit of tweaking of the algorithms and a little bit of tuning. As you saw on the Netcatch video, with the multirotors, they were moving closer to each other and away from each other. And we now have it much more stable. It's able to take larger accelerations without losing the formation or without big errors in the formation. We have also had some problems with time lag of the RTK GPS. And that's especially during the tuning of the formation controllers, because we need it to be very aggressively tuned, and if we have a 0.1 or 0.15 second delay of the RTK GPS, we might not be able to achieve that. And then lastly, a telemetry link. As you saw, the plane was very small, and we want to test with a small plane first in order to not wreck a 2,000 euro X8, because there was a little line in the code that didn't work in real life. But we don't have room for the nice ubiquity modem or the Dune payload in the plane. So for now we have a small telemetry link where we found a good solution, so we can have the Dune part of the plane on the ground. And some future work in this project is to do automatic takeoff and landing of the multirotors, so that we can automate the whole process of the landing, do some more development and testing in order to actually get this to be stable enough to use on ships. And then upscale, of course, we want to be able to catch the X8, and we have a platform, a DJI S1000 platform for doing that. So that is, the next things coming. So, any questions? Thank you. Yeah. Yeah. So in the Linecatch, release the hook from the plane. That's what you're asking? Or yeah. We have a little pod. We have a prototype on a 3D printed enclosure where you can open and release a hook, and you can also so that you can take off without the hook hanging under the plane, and you can do your mission without any risk of the hook getting tangled into the propeller, which is also a very real risk. So it can open and let the hook out as soon as you want to land. And it can also release the wire, like the string and the hook, so you can release it if you're going to belly land instead. Yeah. Yes, yeah. That is the plan, but that is not probably not the next step. Yeah. So I think the next step will be to do the takeoff autonomously and the flying the plane back to the landing spot, and possibly also land the plane autonomously, because we have sensors measuring the weight from the net, so you can descend slowly and then you can measure when you actually landed the plane and release the wires. But landing of the multirotors, I think the next step would be to be able to do that in a formation, so we can have one pilot, multirotor pilot, doing the whole thing. And then after that, of course, you would want to do it autonomously, so that the pilot is just there for safety. But that's, of course, a big challenge. And on a ship, yes, yeah, absolutely. Yeah. Yeah. Yes, so the plane and the multirotors communicate with each other, or the plane communicates its position and velocity to the multirotors, and it doesn't get anything back necessarily. We don't need, the plane doesn't need to be instructed in anything. We're doing it on like a ubiquity network, which is kind of like time-divided Wi-Fi. So for now, I guess it's through the ground station, if I understand it correctly. But I'm not sure.
So the GPS, the position is relayed, the GPS signal is relayed to the
Yeah, so you can, when we've tested it, we've actually used the same computer for both ground stations. So all for the ground control software, and then it's all in a network kind of.
It's just a file, for instance, that continually updates the GPS location, and the multi-rotor autopilot reads that file.
You send it over the network to the, yeah, so you don't store it on the way from the plane to the multirotors, you just send it through the network there. As far as I understand those ubiquity networks, and maybe you guys know, then it works like a Wi-Fi network where you have one node that's set up as a router, and then you connect the devices to them. So it's through that router node, which is on the ground. Yes. Yes, yes, yes. They could, but they are not doing it directly so far. Yes, yeah. Yeah, yeah, yeah. Getting the RTK GPS position on time for the copters is mostly the problem, not so much the plane position. There's a time delay in the processing in the RTK lib from you actually get the GPS signal until it goes through this algorithm and goes through all the communication to Dune and yeah.
Have you considered doing a vision-based? Yeah. Because the reason I say that is because this would really be nice for drone security, like being able to catch a rogue drone.
Yeah, yeah, yeah.
If you have a drone coming into your airspace that you don't want, you can have these two guys that
Yeah, 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 yeah.
you wouldn't have their signal. That have to be vision-based.
Exactly. So yeah, it's basically there's no research on it, but we have thought about doing it, and like as far as I understand, you can get very good stereo vision by probably having a camera on each of the drones, and they'll be far apart, so you can get very good depth perception. Sorry? Yes. Yeah. 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 Yes, they are using RTK GPS to keep their formation. Yeah, they are, like the controller uses the RTK GPS of each one, and they are doing I forgot the right term, but they are kind of agreeing on where to go. So if there's an error, they'll both move. So, yeah. Oh yeah, with the wire. Yes, 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 yeah, yeah, yeah. Or you could have some other, like I don't know, ultra wideband, something ranging just between them in order to keep the same range, and then you could maybe the orientation of your formation you would lose that, or you could lose that if there's an error, but you keep this a fixed distance at least. So yeah, there's multiple ways to do it, and yeah. A lot that can be looked into.
Okay, we finished.
Sure. Thank you.